Welcome back. So in this video lecture, we will look at the GUI-Chapman-Stern electrical double layer model. Okay. This model considers both the parallel plate as well as diffuse boundary layer assumptions. Okay, and we can look at how we can continue to use this the GUI-Chapman model by making some slightest modification in the equation. Okay. Apart from this, we will also look at the how to determine the debye screening length, right, for given electrolyte strength, right, and the temperature. So let's begin. Yeah. Yeah. So before we move on to the electrical double layer model governed by GUI-Chapman and Stern, we can look at first the linearized Poisson-Boltzmann equation, which actually missed during the last lecture. So the equation that we obtained in the form of psi, del square psi equal to k square psi is actually a linearized equation. Okay. Because the k is obtained from the Boltzmann distribution function, the equation that we obtained in this using this approach is called as the linearized Poisson-Boltzmann equation. Okay, so this actually this is actually a very important one. We forgot to highlight this during our last lecture. Kindly make a note of it. Yeah, we'll now move on to the next electrical double layer model. So the GUI-Chapman-Stern double layer model is given here. So what the GUI-Chapman-Stern model considers is the both parallel plate as well as the diffuse double layer. So you have parallel plate as well as the diffuse double layer assumption, okay, given by GUI-Chapman. Because you are incorporating both the parallel plate as well as the diffuse double layer assumption, this particular model is called as GUI-Chapman and Stern model, right? And in this you can see, so the GUI-Chapman considers only the diffuse counterions, right? Uh, Whereas the Stern considers this model, which is combination of GUI-Chapman and Stern considers that there exists both strongly bound counterion, okay, right after the charged surface, and then followed by the diffuse layer. Okay, so he uses the combination of this assumption, that is there is a linear variation right after the charged surface, and then exponential variation after the once the diffuse boundary layer starts to occur, right. So since it is a combination of parallel plate as well as the diffuse layer, we can call this as a GUI-Chapman-Stern layer. Okay, in this case, the slightest modification that is made in the equation is the you just have to subtract the distance x with the xh. This is the distance covered by the Stern plane, right. So in this Stern plane, there will be a linear variation of potential, right. So that if you subtract from the x and the and whatever we evaluate in the form of psi is going to be your GUI-Chapman-Stern model. Okay, so that is the that is a small change that that we have to incorporate into this model, right? Right. Okay. So now we will have to look at the what is the influence of the electrolyte, right? So we are talking about there are going to be variation, right? That is so for brevity we have made psi by psi naught. Okay, so the maximum will be 1 because psi cannot be more than psi naught, and whatever we get is the fraction, right. So here you can look at the figure A and figure B. in the figure A, you can see that there is symmetrical electrolyte is defined here. Okay, figure A, we have given the for the case of the symmetrical electrolyte, let's say 1:1, right? And as a function of the the concentration of the electrolyte, okay, if you change the concentration of electrolyte, keeping the type of electrolyte the same, right, how the fraction of double layer potential varies. That is what exactly shown in the figure here, displayed by the figure A, right. So you can see that as the concentration of salt goes up, the variation, right, uh, that is the variation of psi by psi naught, uh, which is uh, covered by, as a function of distance, right, is also changing, right. You can see for the case of the highest salt concentration here, the distance up to which the fraction of double air potential uh, you know uh, is varied is actually less, right, as the salt concentration is increased. So this can be attributed to the screening of electrostatic charge. I mean, screening of the charges by the salt concentration, right. So on the other hand, in the case of figure B, you can see that for different electrolyte type, let's say you have 1:1, 2:2, 3:3, and keeping the electrolyte concentration also, you can actually show that the variation of the fraction of double layer potential is varied across the surface. Okay. So this can be explained based on the equation that we have. There in the equation, we know there is something called Ni infinity. This is the bulk concentration. Okay. And there is something called Zi square. This is nothing but valence. Okay. By tuning the the bulk concentration, keeping the valence constant, also the one can show that the potential will be affected, right. On the other hand, by keeping the bulk concentration same and varying the valence, right, in this case the valence is varied because we change the type of the electrolyte from 1:1 to up 1:1 up to 3:3. In this case, we actually tune the valence. That's why the the potential, the fraction of double air potential is also varying. Okay, right. So now we can look at the physical significance of the Debye-Huckel parameter. Okay, as you can see, Debye-Huckel parameter, which is k square, is defined in this way, right. Here the variable is the valence, that is Zi square, and the Ni infinity, which is the bulk concentration. Okay. Remember, it is often easy to keep Ni infinity in this form, so that whenever we deal with the problem, we deal with the molarity, right. So we express the concentration of salt in the form of molarity or moles per meter cube. Okay. So it is desirable to have equation of Na infinity in this form as described here. So you can actually uh, you know uh, s- uh, replace Na infinity with the molarity data. Okay, right. So here Mi represents molarity, okay, which is again variable. Na is the Avogadro number, which is a constant. The 1000 multiplier is applied here because Mi is expressed in terms of moles per liter. We want to keep it in the SI unit, that is moles per meter cube. Okay, right. Now the although we obtained the k, which is Debye-Huckel parameter in the equation, sometime we will be it will be interesting to know what is the k inverse, which is nothing but the inverse of k, 1 by k. Okay. So this k inverse is often defined as d by screening length. Okay. So this is actually characteristic length of diffuse boundary layer. So often you will be asked to find out what is the k inverse. So what does it tell is, let's say if you have some charge system, okay, and you have the let's say it is negatively charged solid rigid body, and you will have the counter ions which is strongly bound, right, to the surface. Okay. Then you will have the diffuse layer. Okay. But the variation after some point, okay, will not be pronounced. There will be no variation after some point, because so what does it represent? I mean, what does it indicate is, within this zone there will be variation of the potential. After this zone, uh, you know, no matter how strong the surface is, right? The charge of the surface is, ion present in this zone. Let's say if there is some counter ion present here, okay, which is, let's say, positive, and will not have any will not be influenced by the surface at all. So that is the understanding. So beyond this domain, no ions will be interacting with the surface, the charge of the surface, right? Okay. Or you can say this this charged surface cannot influence any ions, any counter ions or co-ions present after this domain. I said there will be co-ion as well, counter ion also. So there will be no interaction between these ions present after this domain, distance called k inverse, right, and the surface, the charged surface, right. So that is the understanding. So it will be interesting to know what is the the characteristic length of this diffuse layer, that is indicated by what is known as k inverse, which is nothing but d by screening length. Okay. So sometimes it is very important to know what is d by screening length for a given problem. Okay. So that's why we need to do this exercise. How to determine the k inverse, which is inverse of k. So k inverse is actually expressed in terms of unit of length, which is meter. Okay. So this you should know, right? Okay. So now what we can do is, we can actually solve understand one problem tutorial. So we have a tutorials. We will see the tutorial session now. Okay. And here the problem is to determine the d by length. Okay. Okay. So what is k inverse is what we have to calculate for a given concentration, that is 10 moles per meter cube aqueous solutions. Okay. So you make this aqueous solution 10 moles per meter cube based on these three salts. One is NaCl, which is 1:1, and Cl2, which is 2:2, and 3:3, right? So this is what we are going to look at. So remember, in this problem, accepting this part, so if I incorporate this Ni infinity over here, I will have Mi instead of Ni infinity, and Na multiplied by 1000 will be outside this summation, right. So all this will be a constant. Okay. And accepting the Zi and Mi, rest of the terms will be constant. So what you can do, accepting this 1000 multiplier, so we are not use the 1000 multiplier because the problem is given in moles per meter cube itself. So you don't need to multiply that with the 1000. Okay. So what you have is the, here this Mi here is the moles per meter cube itself. Okay. Yeah. So rest of these constants can be grouped into one bracket, and that is nothing but 5.404 into 10 power 15. Okay. So what you need to do is you need to just evaluate only this particular term given within this summation, right? That is nothing but zi square mi. Okay, let's take an example. Now this is going to be constant going to come as it is. Now for this case, how we can calculate? So how you can expand this? So we know NaCl. So Na, so you got two species, one is sodium and another one is chlorine. Okay. So we know the valence of sodium, that is 1 square, okay, multiplied by Mi is given as 10 mole per meter cube, okay, plus the valence of chlorine is also 1, right? The valence of chlorine is also 1. So 1 square, you can say if, so yeah, even if you take minus 1 square, it will be plus 1 square, plus 1 only. No need to worry about any sign over here. So 1 square multiplied by Mi is again 10. So eventually you will get 20. Okay. So if you simply multiply this with this, you will get an answer. In this case, it's a very simple problem. In the case of the 1:1 electrolyte, we don't have to really worry too much. So here the answer is K inverse is 3 nanometer. Okay. 3 into 10 power minus 9 meter. Okay. Right. So this is done. Now, what about the calcium chloride? So the calcium chloride also can be calculated in the same way. Here, so this the rest of the thing will come as it is. Okay, that is 5.404 10 power 15 will come as it is. So when you expand this, okay, the valence of calcium is 2 in fact. So that is 2 square multiplied by Mi will be 10 mole per meter cube, okay, plus the valence of chlorine is actually 1 square, but remember we have 2 chlorine atoms here, so you have to multiply with the 2, and the molarity is given, that is 10 moles per meter cube, right, in this case. So if I just simply sum this, I will be getting 40 plus 20, that is 60. Okay. If I multiply this 60 with this prefactor, you will get the answer, that is the nothing but K inverse, which is given in terms of nanometer, that is 1.76 nanometer. Okay. Right. Right. So we had, in the case of NaCl, we had 3 nanometer. In the case of calcium chloride, it is 1.6 nanometer. Okay. How do we calculate aluminum chloride? So in this case, so it is again same. So it will come as it is. So you have aluminum, the valence is 3 square into 10, plus the valence of chlorine is 1 into 3, because we got 3 atom, okay, into 10, right. So this will be 90 plus 3 into, so this will be 120, okay. So this will be 120, and if I multiply this with this number, I will get 1.24 nanometer. Okay, if I get this, so for aluminum it will be 1.24 nanometer. As you can see, as the electrolyte type is varied from 1:1 to 1 up to 3:3, you can see that the screening length, that is K inverse, actually decreases. This is because the valence is now affected. Although the concentration of salt is same, what is now affected is the valence, right. So that's why the K inverse is also changing. Okay. So this is how you have to determine what is the Debye screening length, okay, for a given problem. There can be many more application that you may come across based on the information given here, that is K inverse, right, that is D by screening length. This problem I have given here, given here for you to do this exercise yourself. Okay, so this is again to determine the D by length. Okay, but the concentration is given in two cases. One is 1 mole per meter cube and the other one is 10 mole per meter cube. And in the aqueous solutions of magnesium sulfate at 298 Kelvin. Okay, so I leave it to you to do this exercise by yourself. Okay. The next tutorial that we can look at is the generate the potential profile. Okay. So considering that the variation of potential with the distance from the surface, right? Okay. In a 1 mole per meter cube NaCl solution at 298 Kelvin, the surface potential is given. So that is psi naught is given here. So psi naught is going to be 150 millivolt. Okay. So we want to understand how the surface potential varies across the surface. We know what is psi. Psi is nothing but psi naught exponential minus kx. Okay. So we need to calculate what is k first, and then for different sets of x value, how the value of y also changes. That is exactly we want to show. Okay. We will see that now using the Excel. Yeah, so let's say we have come here. So maybe we can do this part later. Okay, yeah. So first we know what is the psi naught, which is 150 millivolt. Okay, and so this is again psi. This is psi. Let me put this symbol for you so that this will be clear. Yeah, so this is psi. I will write this as this one, right? So this one. Okay, here there will be no psi naught, right? Yeah. All right. So the psi naught value is given, that is 150 millivolt here, and we need to evaluate what is K inverse. Okay. So K inverse we know for this case, that is the so we are only considering one case, that is 1 mole per meter cube NaCl solution. Okay. For this case at 298 Kelvin, the K inverse is 9.58 nanometer. So K will be inverse of K inverse, right? So that will be 0.104 nanometer inverse. Okay. So now when you for different x values, that is going from 0 up to let's say 75 nanometer distance, right? Okay, across the surface. What is the psi value? Psi also varies, right? So at x is equal to 0, psi will be 150 millivolt. Okay, that is so we are going to start from the surface potential and how it is varying across the surface. Is that what I mean? That is what we are going to look at. So how do we do? So we have actually incorporated this formula here for you. So this is nothing but psi as a function of psi naught into, so psi is going to be psi naught exponential minus kx. That is what we expressed here. Okay, all right. So when you do this calculation for different x, you get this psi. So if you just plot this x and psi, you basically get this equation. All right. So this is the potential variation across the psi, across the surface, as a function of x, which is a distance, okay, which is given in nanometer. X is given in nanometer, okay, and psi is actually given in millivolt. So this is actually given in millivolt. So how the surface potential varies across the surface, that is what exactly we are looking at. After about 70 nanometer, the psi is almost 0, which means that you know, so is away, far away from the surface, right? Is far away from the surface, so it is approaching the bulk concentration, right? So that is exactly what we can understand from this. All right. So we can stop here. We can continue from the next lecture. Thank you.